Welcome to the design of pipelines, and in this particular chapter we are going to discuss about the natural gas transmission. Let's have a brief outlook about what we discussed in the previous lecture. We discussed about the natural gas transmission. We derived the general flow equation in steady state with respect to the kinetic energy term, with respect to the pressure energy term, potential energy term and friction loss term. In this particular lecture, we are going to discuss about the various flow regimes, including fully turbulent flow, that is rough pipe flow, partially turbulent flow, that is smooth pipe flow, pressure drop calculation. We will discuss the pipelines in series, pipelines in parallel, pipeline in segmental looping. Now, let us talk about the flow regimes. Now, in high pressure gas transmission lines with moderate to high flow rates, there are two types of flow regimes which are normally observed. One is the fully turbulent flow, that is rough pipe flow, and second one is the partially turbulent flow. So, the regime of flow is defined by the Reynolds number and which is dimensionless, and Reynolds number is Re is equal to rho du over mu. Now, here if we see that the term used in the Reynolds number, that is rho is equal to fluid density in kilogram per meter cube. D is the pipe diameter or pipeline internal diameter. M. U is the fluid average velocity in meter per second, and mu is the fluid viscosity, that is kilogram per meter second. Now, if Reynolds number is less than 2000, the flow is normally laminar or stable. Now, if Re is greater than 2000, the flow is turbulent or unstable. In high pressure line only two type of flow regimes exist, fully turbulent or partially turbulent flow. Now, let us talk about the partially turbulent flow regime. The partially turbulent flow is defined by the Prandtl-von Karman equation, and this equation is square root of 1 upon f is equal to 4 log to the base 10 Re upon 1 upon f minus 0.6. Now, where f is the friction factor, R that is dimensionless, and Re is the Reynolds number. Now, it is applicable in which the flow is fully turbulent in the center region of the pipe with a laminar sublayer covering the interior surface of the pipe. Now, here you see that it is a semi-log graph where the straight line shows the maximum limit of partial turbulent flow. Now, all points to the right hand side of the line, this exhibits fully turbulent flow, and left hand side remain partially turbulent. This is the fully turbulent and partially turbulent zones by a Prandtl-von Karman equation. Let us talk about fully turbulent flow regime. The transmission factor for fully turbulent flow is given by Nikodym's equation, which is as represented. 1 upon f is equal to 4 log to the base 10 3.7 d upon Ke. Now, where 1 upon f, this is the transmission factor which is dimensionless in nature, d is the pipeline internal diameter, Ke is the effective roughness, that is represented in m, and Ke upon d is the relative roughness, that is dimensionless. Now, this Ke, the effective roughness term, this can be defined as Ke is equal to Ks plus Ki plus KD. Now where Ks is the surface roughness, Ki is the interfacial roughness, and Kd is equal to roughness due to bend, fitting, sometimes they are very common, and welds. Now with high pressure gas transmission lines with high flow rate and fully turbulent flow regime, and natural gas is almost dry, and Kd and Ki are negligible if we compare with Ks. Now the values of Ks and Ke is very important in fully turbulent flow regime without the laminar sublayer. The surface roughness of the pipe play important role in determining the flow and pressure drop. The Nicholson equation shows that if the effective roughness of the pipeline is increased, the transmission factor decrease and its result in high pressure drop. So for internally uncoated commercial pipe where this Ke is unavailable, 700 micron inch may be assumed. Now the calculation of Reynolds number in gas transmission system, Re in gas transmission system. So this Re is equal to rho d u upon mu, u is equal to q upon pi d square by 4, where Re is equal to rho d q upon mu pi d square by 4. Now at steady state condition, rho q is equal to Pb Qb. This is then Reynolds number is equal to 4 Qb rho b upon mu pi d. Now if rho b is equal to Pb m upon Zb Rtb, for natural gas, value of Zb is equal to 1 and m is equal to 29 G. So Re is equal to 4 Qb 29 G Pb upon mu pi dRtB. So on substitution of value of variables, pi R is equal to 10.73 psi cubic feet per pound moles R, Pb is equal to 14.7 psi, mu is equal to 7.23 into 10 to the power minus 6 pound meter per second. The Re is equal to 45 Qb G upon D. Now Qb is equal to gas flow rate in cubic feet per hour. G is equal to gas gravity, that is dimensionless. D is inside diameter of pipe, that is in inch. Now this is the simplified equation, and that gives the Reynolds number in terms of pipeline parameter. Now let's talk about steady state flow equations. Flow equations. So the general flow equation of natural gas in pipeline is given by Qb is equal to pi RGC upon 1856 ZB TB upon PB P1 square minus P2 square minus 58 G delta H average P square upon RT average Z average upon 58 Z average T average GL 1 upon F d to the power 2.5. Now assume potential energy term, that is E is equal to 0.0375 G delta H average P upon T average Z average. Then we have upon simplifying we get QB is equal to 38.774 TB upon PB 1 upon F P1 square minus P2 square minus E upon Z average T average GL d to the power 2.5. Now this is the most common and widely used flow equation, and that is suitable for design of large diameter high pressure gas transmission line. Now let's talk about the partially turbulent equation. Now Panhandle equation. This equation is normally used for medium to relatively large diameter pipeline with moderate gas flow rate operating under medium to high pressure. Now here we can see that QB is equal to 435.83 TB upon PB to the power 1.0788 into P1 square minus P2 square minus E upon G to the power 0.8539 Z average T average L to the power 0.5394 D to the power 2.6182. Now the transmission factor is defined as 1 upon F 6.87 RE to the power 0.07305, or this can be 1 upon F is equal to 7.211 QB G upon D to the power 0.07305. Now we can link all these parameters which we have discussed earlier. Now AGA partially turbulent, this AGA partially turbulent equation is highly dependent upon Reynolds number. Now this equation is used for medium diameter and medium flow and high pressure system. Now let's write this particular equation. This QB is equal to 38.774 TB upon PB, P1 square minus P2 square minus E upon G Z average T average L to the power 0.5 4D F log RE upon 1.4126 square root of F D 2.5. Now the transmission factor is defined as 1 upon F is equal to 4D F log RE upon 1.4126 square root of F. Now where DF is drag factor, normally appears in the partially turbulent flow equation, and its numerical value is ranging from 0.92 to 0.97. Now the Panhandle B, this equation is suitable for high flow rate, large diameter and high pressure system. Now this equation can be represented as QB is equal to 737.02 TB upon PB to the power 1.02 P1 square minus P2 square minus E upon g to the power 0.961 Z average T average L 0.5 d to the power 2.53. The transmission factor is usually defined as 1 upon f is equal to 16.70 qbg upon d 0.01961. Now the efficiency in Panhandle B equation is defined as Q actual upon Q theoretical. Now it is multiplied in the equation to calculate more accurate value of QB, and all the parameters in the main equations are same as per the which we have discussed. Now let's talk about the Weymouth equation. Now this equation is used for high flow rate, large diameter and large pressure system. This equation is helpful in pressure drop prediction and contains low degree of accuracy relative to other equation. So this is used in the distribution network for safety in predicting the pressure drop. Now this equation can be written as QB is equal to 432.7 TB upon PB, P1 square minus P2 square minus E upon G Z average T average L to the power 0.5 D 2.667, and the transmission factor can be defined as 1 upon f is equal to 11.19 d to the power 1 by 6. Now let's talk about the AGA fully turbulent equation. It is most frequently and widely used equation in high pressure, high flow rate system for medium to large diameter pipeline. It will help to predict the flow rate and pressure drop and also effective roughness values with high degree of accuracy. So this equation is again represented as QB is equal to 38.774 TB upon PB, P1 square minus P2 square minus E upon G Z average T average L 0.54 log 3.7 D upon KE D to the power 2.5, and the transmission factor can be defined as 1 upon F is equal to 4 log 3.7 D upon KE. Now another equation is Colebrook-White. Now this equation used for both partially turbulent and fully turbulent flow regime and also suitable when a pipeline is operating in transition zone. So it is used for large diameter, high pressure and medium to high flow rate system. Let us write this particular equation. QB is equal to 38.774 TB upon PB, P1 square minus P2 square minus E upon G Z average T average L 0.5 minus log 4 log 3.7 D KE plus 1.4126 1 upon F upon RE D to the power 2.5. Now it predicts high pressure drop and low flow rates than AGA equation. Now for this we need to define the transmission factor. So the transmission factor 1 upon F is defined as minus 4 log 3.7 D upon KE plus 1.4126 1 upon F upon RE. Now let us go for the pressure drop calculation for pipelines, because pressure drop is a very common phenomena in the pipelines. So there are two cases. One is the pipeline in series, and another one is the pipeline in parallel. So the pipeline in series with a different diameter and length, the pressure drop can be calculated in a very generalized flow equation like P1 square minus P2 square is equal to K1 QBN. P2 square minus P3 square is equal to K2 QB to the power, and then P3 square minus P4 square is equal to K4 QB to the power n, where K1, K2, K3 these are the pipeline resistance at each segment, and n is the flow exponent depending upon the type of equation used. Now here we represented this in the form of pictorial diagram. Here the P1, P2 and P3, P4, these are the pressure regime, and D1, K1, QB, this is the parameters at this juncture, and D2, that is the diameter, K2 QB is this juncture, and D3 K3 QB at this juncture. So if three equations are added together, then we get P1 square minus P4 square is equal to K1 plus K2 plus K QB to the power n, and KT is equal to all K's to be added. So if we combine these two equations, then we get P1 square minus P4 square is equal to KT QB to the power n. Now let's talk about the pipelines in parallel or looping. So we need to consider that two different pipes are connected in parallel, as was shown in this figure, QB P1, QB1, QB2, and these are the two pipelines, K1 and K2, D1 and D2, and P2 is the outlet temperature. So the governing equation for pressure drop off for each segment will be represented as P1 square minus P2 square is equal to K1 QB1 n. Now P2 square minus P3 square is equal to K2 QB2 to the power n, where QB1 plus QB2 is equal to QB, and generally P1 square minus P2 square is equal to K QB to the power n. Now K is the total resistance of a pipeline, of a pipe substituted for loop. So if we rearrange the above equation, we get QB1 is equal to P1 square minus P2 square upon K1. Now similarly, QB1 is equal to, or QB1 is represented as minus P2 square upon nth root of K1, and QB2 is equal to nth root of P1 square minus P2 square upon nth root of K. And the general equation can be represented as QB is equal to nth root of P1 square minus P2 square upon nth root of K. Now if we substitute the value of QB1, QB2 and QB, we have nth root of P1 square minus P2 square upon nth root of K, that is equal to nth root of P1 square minus P2 square upon nth root of K1 plus P1 square, nth root of P1 square minus P2 square upon nth root of K2. Similarly, K is equal to K1 K2 upon K1 to the power 1 over n plus K2 to the power 1 over n. Now if n is equal to 2, this above equation giving the total resistance of a two pipeline in parallel, and which can be given as K is equal to K1 K2 upon K1 to the power half plus K to the power half square, where K is the total resistance of two pipeline looped together. Now, if two pipeline have equal diameter, then K is equal to 1 upon 4 K1. Now, let's talk about the pipeline segmental looping. Now, segmental looping, it is not necessary to loop the entire pipeline to obtain the desired flow or downstream pressure, but only segment of the pipeline is looped to meet the requirement. Now, let us assume that the pipeline has the length L and diameter D, and the total resistance is K1 plus K1 dash, and the inlet and outlet pressures are P1 and P2. Now, to increase the existing gas flow rate from Q1 to Q2 without any change in the downstream pressure, the value of X, that is the length of the pipeline to be looped to existing system, must be determined. Now, by using the larger diameter pipes, the required length of the segment to be looped is usually reduced. Now, Weymouth equation can be used to obtain total pipeline resistance, which is start with one of the major transmission equation and continue to develop the equation to calculate the length of the loop. So, again coming back to Weymouth equation, that is P1 square minus P2 square, and that is equal to 0.000466 G TF upon L over D 16 by 3 Q1 square, or P1 square minus P2 square is equal to K Q1 square, where K is equal to K1 plus K1 dash. This is the total resistance of the single line. For the total resistance of Weymouth equation, the value of 0.000466 GTF is constant and named as C. Now, K1 is equal to Cx D1 16 by 3, K2 dash is equal to Cx upon D1 16 by 3, K1 is equal to Cl minus x upon D1 16 by 3, and K is equal to Cl upon D1 16 by 3. The equivalent resistance for looped segment is Ke is equal to Cx upon D1 16 by 3, Cx is equal to D2 16 by 3 upon Cx D1 16 by 3 plus Cx upon D2 16 by 3 whole square. Now, if we simplify, then Ke is equal to Cx D 16 by 3 D1 D2 16 by 3 whole square. Now, Ke total is equal to Ke plus K1. So, if we rearrange for Ke, then Ke becomes Cx upon D1 16 by 3 plus D2 16 by 3 square plus C L minus x upon D1 16 by 3. Now, upon dividing the flow equation for existing pipeline after segmental looping, we have P1 square minus P2 square upon P1 square minus P2 square is equal to D1 CL D1 to the power 16 by 3 upon Ke Q1 upon Q2 square, or 1 is equal to Cl D1 to the power 16 by 3 whole upon Cx upon d1 16 by 3 plus d2 16 by 3 whole square plus c L minus x upon d1 16 by 3 q1 upon q2 whole square. So, the equation becomes x is equal to L q1 upon q2 square minus 1 upon 1 plus d2 8 by 3 upon d1 minus 1. Now, where x, that is the length of pipeline to be looped, that may be in miles, L is the length of existing pipeline in miles, Q1, that is the initial gas flow rate, Q2 is the final gas flow rate if you see, and D1 is the existing pipeline inside diameter in inches, and D2 is the looped segment inside the diameter, which is represented in inch. Now, this equation demonstrates that the looping will increase pipeline flow capacity without any changes to the upstream and downstream pressures. Now, there are two important parameters which we need to consider when choosing the location for a pipeline loop, that is temperature and pressure. So, at last in this particular segment we discuss the various pipeline configuration, series and parallel. We devise the equations with respect to the other parameters in question. For reference, we have enlisted a reference for your convenience. Thank you very much.